running the kubectl command. It says kubectl command not found. Let's go. Hello and welcome. Let's continue where we left off in our previous demo. So let's get started. Now the next step is to install kubectl. kubectl is a command line utility that helps us interact with our Kubernetes cluster. In our previous demo where we used Cloud Shell to access Kubernetes cluster, the kubectl utility comes pre-shipped with the Cloud Shell machine. In this case, the kubectl is not installed on my local machine. We can confirm that by running the kubectl command. It says kubectl command not found. Let's go ahead and first install kubectl packages. I'm referring this documentation over here to install and set up kubectl. In my case, it's a Linux terminal, so I'll select Linux and let's copy the curl command to download the latest release. Let me head back to my local terminal and paste the curl command. Let's hit enter. All right, so the package has been downloaded. Let me do an ls. Confirm if the kubectl package has been downloaded. Next thing is to make the kubectl binary executable. Let's run the chmod command. Let's hit enter. And finally, we must move the binary into your path variable, which is usr local bin kubectl. Let me copy this command. Paste it here. All right, so our kubectl has been installed and configured. Let me run a kubectl command again. And as you can see, it gives me all the options, which means kubectl has been configured correctly. Let me clear the screen. Just to check the kubectl version installed on my local terminal, let me run the kubectl version command. And the version that it's running is 1.28.4. Let me clear the screen. All right, so now that we have configured OCI CLI, installed kubectl, and also copied the public API signing key pair to our OCI console, the next thing that I'll be doing is now setting up the kubeconfig file. So let's go back to our OCI console. Let me go to the Kubernetes cluster page. Let's click on developer service. Let's go to Kubernetes cluster. Let's click on the cluster from the cluster list page. Let me click on access cluster this time. And this time around, we'll be using the local access. So let me click on local access. And let's follow all the steps given here. By far, we have already downloaded and installed OCI CLI. We have configured it for use. And as the information says that the OCI CLI version must be 2.24.0 or later. And in our case, it's the later version. The next thing that we'll be doing is to create a directory to contain the kubeconfig file. Let me copy this command and let's head back to our local terminal. Let me paste that command over here. This creates a hidden kube directory in my home directory. Let's hit enter. Let me go to the home directory and let's do an ls. And as you can notice, we have this .kube directory created. Now the next command that I'll run is to access the kubeconfig file for our cluster via the VCN native public endpoint. Remember, our cluster's Kubernetes API endpoint is in a public subnet for which I'll be copying this command. Let's head back to our local terminal and paste the command here. Let's hit enter. And it says a new config has been returned to the kubeconfig file, which is available in the .kube directory that we just created. So let me go to the kube directory. Let me hit enter. And if I do an ls here, you can see that the config file is created. Let me open up the config file for you. As you can notice, it has all the information like the cluster OSID. The cluster OSID ends with DPQ. Let me head back to our OCI console. Let me close this. And just to confirm, our cluster OSID is ending with the letters DPQ. This is the cluster that we have created access to from our local terminal. Now that we have set up the access, The last step is to verify that the kubectl can access the cluster, for which I'll be running the kubectl get nodes command. Let me hit enter. And there you go. From the output, we can see that it has returned us the list of worker nodes. And this confirms that we were successful in setting up local access to our cluster Kubernetes API endpoint in the public subnet. Now let me run a command with inline configuration to create a deployment within the Kubernetes cluster. The command is kubectl create deployment. Let's give the deployment a name. This is Mahindra-Nginx. Let's provide the container image. Let's set the replicas for the pod to 2. Let's hit enter. And it says the deployment is created. Let's check whether the pods are in action. So let's do a kubectl get pods command. And there you go. We can confirm that the 2 pods as part of our deployments are in the running state and have been created successfully. Well, that's it from this demo where we saw how to set up local access to our cluster. I hope you enjoyed the demo. See you in the next one. Thank you so much for watching. Hello and welcome to this lesson on OCI DevOps service. Before we define the specifics of OCI DevOps as a service, let's generally define the DevOps in the cloud. DevOps automation is becoming cloud-centric. Most public and private cloud computing providers support DevOps systematically on their platform, including continuous integration and continuous development tools. This tight integration lowers the cost associated with on-premises DevOps automation technology and provides centralized governance and control for a sound DevOps process. DevOps in cloud is a suite of managed cloud-based tools that forms a pipeline for code and bug tracking, automated unit testing and deployment, and reviewing and monitoring. Now, the question is, why use DevOps in cloud? There are several reasons why customers would want to use DevOps in the cloud. Some of those reasons include it saves time and energy. Building DevOps infrastructure requires a lot of work. A pre-built solution will save time and energy. Next is it collapses into single silo for collaboration. DevOps minimizes the silos and gaps by eliminating the boundaries between the conventional developer and the operation rules. This ensures business continuity, accountability, and desired results across groups. DevOps also helps you automate the entire deployment process. It helps you lower cost for development, testing, deployment, and operations. It's much easier to track cost of development resources and make adjustments as needed. Let's understand OCI DevOps as a service in more detail. The Oracle Cloud Infrastructure DevOps Service is an end-to-end continuous integration and continuous delivery platform for developers. This service makes it easy to build, test, and deploy software and applications on the Oracle Cloud. With the help of OCI DevOps Service, you can create private code repositories to store and manage source codes. You can also mirror external repositories from GitHub, GitLab, and Bitbucket Cloud to OCI code repositories. It helps you build and test your latest changes in a build pipeline with a service-managed build runner. You can set up a trigger to automatically run your build pipeline from a source code commit or pull request. Optionally, you can run a deployment pipeline on the successful build run for a complete CI/CD automation. It lets you orchestrate your software deployment across regions to OCI platforms such as Container Engine for Kubernetes, also known as OKE, and compute instances and functions. It helps you avoid downtime during deployments through the blue-green and canary deployment strategies. It helps you automate the complexity of updating applications. Automation reduces the chance of human error that might introduce a security vulnerability. It enhances the security and reduces risk in delivery. As DevOps enables faster software delivery, security bugs can be resolved quickly by rolling out a fix. Let's take a look at some of the DevOps as a service benefits. The first benefit is automation. The OCI DevOps service fully automates the software delivery lifecycle and thereby increases the speed of development and reliability of application delivery. It eliminates manual error prone methods of application integration and deployment and increases the reliability of operations. Next is scalability. OCI DevOps service scales your builds with service managed build runners. You can run concurrent builds and don't need to manage or operate the underlying build runner host. Integration and interoperability. DevOps service works with your existing Git repositories and continuous integration systems for customers building new cloud native applications or migrating existing applications to OCI. The DevOps service is integrated with OCI services such as virtual machines, Oracle Container Engine for Kubernetes, Oracle Functions, artifact repositories, vault secrets, policies, and much more. Low risk of deployments and faster time to market. With OCI DevOps deployment pipelines, you can reduce change-driven errors introduced by manual deployments. Instead, perform rolling, canary, or blue-green deployments and optional automated rollbacks. All these capabilities lead to reduced risk, complexity, and eliminate downtime of your production applications. Last but not the least is the low cost. For deployments, customers pay only for the resources used by the targets of their software deployments. To wrap up, in this lesson we introduced you to OCI DevOps service and discussed the benefits it offers to developers to simplify the software delivery lifecycle. To all the DevOps enthusiasts who wish to get started with the DevOps service, I would recommend that they go through the OCI DevOps professional learning path. I hope you enjoyed this lesson. See you in the next one. Thanks for watching. Hello and welcome to this lesson on OCI DevOps CI/CD. I am Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. So let's get started. Continuous integration and continuous delivery or deployment is DevOps best practice. With continuous integration shown in the blue on the screen, incremental frequent code changes are built, tested, and revised as needed based on constant feedback. The term refers to the fact that these small changes and error fixes are continuously integrated into the code repository. Small frequent changes are easier to manage because errors are small, seen early, and less likely to conflict with other code merges. CI/CD tools trigger automatic, standardized build and test steps that ensure the code changes being merged into the code repository are error-free and work with the existing code. This shifts the focus from problem detection to problem prevention, which is also called shifting left, as it moves code failures to earlier in the process. Early fails are quicker and cheaper to fix. Once the main code branch passes unit, integration, acceptance, and other tests, it is then released to production in either an manual continuous delivery process or an automated continuous deployment mode, which is shown in the green on the image. Continuous feedback, shown in the gray region, is also a key part of the DevOps process. Here's the overall OCI DevOps structure and workflow. Let's take a closer look at the OCI DevOps service offering. OCI DevOps project is a logical grouping of DevOps resources needed to implement a CI/CD workflow. DevOps resources can be artifacts, build pipelines, deployment pipelines, external connections, triggers, and environments. The Developer Associate certification focuses on the services like container registry, OKE, and functions. But having knowledge of the OCI DevOps service like build and deployment pipeline can help you automate the process for continually integrating software development changes. You can learn more about the OCI DevOps service from the official documentation or by exploring the learning path on how to become an OCI DevOps professional. Let's take a look and understand the OCI DevOps workflow right from committing the code changes till its deployment on the live servers. The heart of the workflow is the build and deployment pipelines with continuous integration and continuous deployment. The build pipeline follows a user-defined flow to build the code, test the package, and deliver them as code artifacts in the OCI artifact registry or as ready to ship image in the container registry. The deployment pipeline then uses the built image from the container registry and a Kubernetes manifest to deploy the most recent version of the application to a staging environment. After the final tests and approvals, the pipeline pushes the image to the desired production environment, which can be a group of compute hosts, a container engine, or a function, completely based on the architectural design of the software application. You might also want to move an existing application from on premises or another cloud to OCI and move software delivery and deployments to the OCI platform. The OCI DevOps service also has the flexibility to integrate with your existing CI CD workflows. To wrap up, in this lesson we covered the OCI DevOps CI CD pipeline and using an illustration saw how a CI CD pipeline automates your software delivery process. I hope this lesson was useful. Thanks for watching. Welcome to this lesson on Oracle Functions Overview. I am Mahendra Mehra, Senior OCI Instructor with Oracle University. And in this lesson, we'll explore how Oracle Functions streamlines serverless computing with robust performance, security, and cost efficiency. So let's get started. Trisha, an Oracle client who's working on a new project, seeks advice on the best cloud solution to use. Steve, an Oracle consultant, greets her warmly and offers his assistance. Trisha explains that her team wants to focus on developing their application without worrying about infrastructure management. They also need a solution that can handle sudden spikes in traffic seamlessly, ensuring optimal performance without constant scaling adjustments. Steve suggests that Oracle Function might be a great fit for her project and asks if she is familiar with serverless computing. Trisha admits she has heard the term but isn't exactly sure what it means. Steve explains that although the term serverless can be misleading since it involves servers, these servers are managed by cloud providers, so users don't need to configure or maintain them. Intrigued, Trisha asks how it works. Steve uses an analogy comparing it to needing electricity for a home. Instead of setting up solar panels, batteries, and wiring, one could simply connect to the local power grid and pay for the electricity used. Similarly, serverless computing involves the amount of CPU and memory needed to run code, managed by the cloud provider. Steve further elaborates it to Trisha, asking her to think about developing an application requiring coordination between developers and operations teams. Traditionally, setting up servers, managing infrastructure, and ensuring scalability would involve extensive collaboration. However, with serverless computing like OCI functions, developers are empowered to create and deploy applications independently, without the need to involve operation teams in server provisioning and management. It's like giving developers the tools they need to build their applications autonomously, streamlining the development process and accelerating time to market. Trisha clarifies, asking if OCI functions simplifies things by taking server management out of the equation. Steve confirms, explaining that with Oracle functions, developers can focus solely on writing their code while the cloud providers handles everything else behind the scenes, which includes choosing the operating system, setting up networking, applying patches, and provisioning capacity to handle scaling. After understanding the concept of serverless computing and how it simplifies infrastructure management, let's take a closer look at Oracle Functions. Oracle Function is a powerful serverless function as a service offering that is seamlessly integrated with Oracle Cloud Infrastructure. This platform allows you to deploy your functions as container images, running them in a container native environment. Built on top of the open source FN project, Oracle Functions ensures robust performance and flexibility. Security is a top priority with Oracle Functions. Your functions are protected using Oracle Cloud Security constructs such as networking, identity and access management, and compartments, among other features. This ensures that your functions operate in a secure and controlled environment. Let's explore some of the key benefits of Oracle Functions. Cost efficiency. Oracle Functions operates on a pay-per-use model. This means you only incur cost when your functions are actively running. If your functions are idle, you don't pay anything, making it a highly cost-effective solution. Autonomous management. The platform is designed to be autonomous. It handles provisioning, management, and auto-scaling of your functions, so you don't have to worry about these operational aspects. This allows you to focus on writing and deploying your code without the overhead of infrastructure management. Event-driven architecture. Oracle Functions is an event-driven platform. It integrates with various OCI services, enabling automatic triggering of your function code based on specific events. This facilitates seamless integration and automation within your cloud environment. One of the key advantages of Oracle Function is that they are packaged as container images and run as containers. This container native approach ensures that your functions are isolated, portable, and scalable. By leveraging container technology, you can encapsulate your function along with all its dependencies, ensuring consistent execution across different environments. With Oracle Functions, you can easily package and reuse open source libraries as part of your functions. This means you can leverage the rich ecosystem of existing libraries to accelerate your development process. By incorporating these libraries, you can avoid reinventing the wheel and instead focus on the unique aspects of your application. Oracle Functions offers function development kits, or also known as FDKs, for a variety of popular programming languages, including Python, Java, Go, Node.js, and Ruby. These FDKs provide a set of tools and libraries to simplify the development, deployment, and management of your functions. For more advanced use cases, Oracle Functions allows you to bring your own Docker file, giving you the flexibility to customize the FN-generated Docker image. This enables you to tailor the runtime environment to your specific needs. Additionally, you can take advantage of the Micronaut microservices framework and GraalVM native image to further optimize your functions. Using Micronaut can help you build lightweight, modular applications, while GraalVM native image can significantly reduce your container image size and memory footprint, resulting in faster startup times and lower resource consumption. To wrap up, in this lesson, we covered the key features and benefits of Oracle Functions, including its serverless computing capabilities, cost efficiency, autonomous management, event-driven architecture, and the advantages of container-native execution. By leveraging these features, you can simplify infrastructure management, accelerate development, and deploy robust serverless applications with Oracle Functions. I hope you found this lesson useful. I'll see you in the next one. Thank you for watching. Hello and welcome to this lesson on functions concepts. I am Mahendra Mehra, Senior OCI Instructor with Oracle University. In this lesson, we'll dive into the fundamental concepts of Oracle Functions. We will start by exploring the key components that make up the functions ecosystem, including the roles of the functions developers, the applications they build, the functions themselves, the invocation of those functions, and the triggers that can initiate those invocations. Let's start by understanding the role of function developers in Oracle Functions. Function developers are the OCI users who create and deploy functions using the OCI Functions service. To work with OCI functions, these developers must have valid OCI user accounts. For function developers to access function-related resources, their user accounts must belong to specific groups, and these groups must have appropriate policies that grant the necessary permissions. These policies ensure that developers can securely and efficiently create, deploy, and manage their functions within OCI environment. Let's delve into the concept of applications within OCI functions. An application in OCI functions serves multiple critical purposes. Firstly, it acts as a logical grouping of functions, allowing you to allocate and configure resources for all functions within the application. Additionally, it provides a common context to store configuration variables accessible to all functions in the application and ensures runtime isolation of these functions. When defining an application in OCI functions, you need to specify the subnets in which the functions will run. You also have the option to enable logging for the functions within the application. This setup not only organizes your functions, but also ensures that when functions from different applications are invoked simultaneously, their executions remain isolated from one another. For better efficiency and performance, it's a best practice to group multiple functions within a single application. OCI functions provides a clear overview of applications and their functions directly in the console, making it easier to manage and monitor your serverless infrastructure. Now let's explore the core concept of functions within OCI functions. Functions are essentially small yet powerful blocks of code, each designed to perform one specific task efficiently. This simplicity makes them highly focused and effective. For better management and resource allocation, functions are grouped into applications. This logical grouping helps in organizing functions and managing their configurations cohesively. Functions in OCI functions are stored as container images in specified container registry. This approach ensures that the functions are consistent and portable and can run seamlessly across different environments. Functions can be invoked in response to a CLI command or a signed HTTP request. This flexibility allows functions to be triggered programmatically or through user interactions. When you deploy a function using the FN project CLI, it is built as a container image and pushed to the specified container registry. A definition of the function is then stored as metadata in the OCI functions server. This definition includes details on how functions should be executed, such as the container image to pull, the maximum execution time, and the maximum memory consumption allowed. Let's discuss how function invocations work in OCI functions. Functions can be invoked through various methods, providing flexibility for different use cases. You can use the function project CLI, Oracle Cloud Infrastructure SDKs, or send signed HTTP request to the function's invoke endpoint. Additionally, functions can be triggered by events from other Oracle Cloud services or even external services. Each function has a unique invoke endpoint, which is used for sending signed HTTP requests. This endpoint is crucial for securely invoking the function from various sources. When a function is invoked for the first time, OCI function pulls the function container image from the specified container registry. It then runs the image as a container and executes the function. This ensures that the function is ready to handle requests as needed. For subsequent requests to the same function, OCI functions efficiently directs these requests to the existing container. This reuse of the container minimizes startup latency and improves overall performance. To optimize resource usage, OCI functions removes the container after a period of inactivity. This means that if a function hasn't been invoked for a while, its container is stopped and removed, conserving resources until the function is needed again. Additionally, OCI functions provides detailed metrics about function invocations through metrics charts in the console. This information helps you monitor and understand the behavior and performance of your functions. Let's discuss triggers. In OCI functions, a trigger is defined as the result of an action elsewhere in the system that sends a request to invoke a function. This allows functions to be executed in response to specific events or conditions. Triggers can be event-driven, meaning they are initiated by events occurring in other Oracle Cloud services. For instance, an event in the event service might cause a trigger to send a request to the OCI functions to invoke a function. This creates a seamless integration between different services within the Oracle Cloud ecosystem. Triggers can also be time-based, where they are scheduled to send regular requests to invoke a function at defined intervals. This is useful for tasks that need to run on a fixed schedule, such as periodic data processing or maintenance activities. A function in OCI functions might not be associated with any triggers, or it could be linked to one or multiple triggers. This flexibility allows functions to be invoked in various ways depending on the requirements of your application. Let's delve into function development kits, or FDKs, which are crucial for OCI functions to support different programming languages. FDKs are essentially a collection of helper libraries designed to handle system internals such as protocols, passing input and output, and the logic necessary for managing function containers. OCI Functions utilizes FN Project's FDKs to provide support for a range of popular languages, including Java, Node.js, Python, Go, Ruby, and C#. Each language's FDKs comprises three key components. First, we have the build time base image. This image contains all the language-specific libraries and tools required to build executable functions. Next, there's the runtime base image. This provides the environment necessary to run the functions, ensuring they have the appropriate runtime support. Lastly, each FDK includes an FDK library. For Java specifically, this library is bundled within both the build time and the runtime base images, streamlining the development and execution process. When you first create a function using the FN Project CLI fninit command, you specify the language in which the function's source code is written using the --runtime command option. You can also optionally specify a version of the language. If you don't specify the language version, the FN Project CLI assumes you want to use the most recent version of the language FDK that's available. The FN Project CLI records the value of the --runtime command option as the value of the runtime parameter in the functions.yaml file. Additionally, it adds values for the build image and the run image parameters according to the specified runtime command option. For example, if you enter fninit --runtime python and specify your function name, which is hello world-function in this case, and if Python 3.11 is the most recent version available, the FN Project CLI adds the following to the function.yaml file. It adds the runtime parameter, the build image parameter, and the run image parameter. If you specify both a language and a version as the value of the --runtime option, the FN Project CLI adds the corresponding version of the language's FDKs, build time, and runtime base images as values for the build_image parameter and for the run_image parameter. As you can see in the example, if you hit fninit runtime python 3.9 and the function name, the FN Project CLI adds the following to your function.yaml file. Here the runtime has been modified to Python 3.9 and the build image and the run image parameters have also been modified to use Python 3.9. If you want to rebuild an existing function that was initially built with Python 3.9 and now you want to build it with Python 3.11, change the values of runtime, build_image and run_image parameters in the functions.yaml file to reference the latest FDK version for Python 3.11. And finally, run the fnbuild function name command to bring the new changes into effect. To summarize, in this lesson we've covered the essential concepts that underpin the Oracle Functions platform. With this foundational knowledge, you are now equipped to further explore the advanced features and use cases of Oracle Functions as we continue our journey. I hope you found this lesson insightful. See you in the next one. Thank you for watching. Hello and welcome to this lesson on understanding functions operations. I am Mahindra Mehra, your senior OCI instructor with Oracle University. In this lesson, we'll explore the operations of Oracle functions, focusing on the process of deploying and invoking functions. So let's get started. Let's walk through the process of deploying a function to OCI functions. Once you've written the code for your function and it's ready to deploy, you start by building a container image from the function. This step packages your code and any dependencies into a container image, ensuring consistency across different platforms. Next, you provide a definition to the function in a function.yaml file. This file includes important execution parameters such as the maximum length of time the function is allowed to execute and the maximum amount of memory it is allowed to consume. After pushing the image, the function's metadata is uploaded to the FN server. This metadata includes the execution constraints defined in the function.yaml file, such as memory and time limits, and a link to the image stored in the OCIR repository. Finally, the function is added to the list of functions shown in the OCI functions console. This allows you to manage and monitor your function directly from the OCI interface. This entire process can be executed using a single command from the FN project CLI, streamlining the deployment workflow and making it easier to get your functions up and running on OCI functions. Let's walk through the process of invoking a function in OCI functions with the help of a diagram. Functions can be invoked using various methods, including the FN project CLI, Oracle Cloud Infrastructure SDKs, signed HTTP requests, and triggers from other Oracle Cloud services or external sources. When a function is invoked, OCI function first verifies the request with the IAM service to ensure proper authentication and authorization. If the request passes these checks, it proceeds to the next step. The request is then passed to the FN server, which uses the function's definition to identify the container image from the container registry. The function is executed by running the image as a container on an instance within a subnet associated with the function's application. While executing inside the container, the function can interact with other resources and services within the same subnet, such as database as a service. It can also access shared resources like object storage and other Oracle Cloud services. The maximum execution time of the function can be specified in the function.yaml file or through the console. OCI functions store the function's logs either in Oracle Cloud Infrastructure or in an external logging destination. After the function finishes executing and remains idle for a period, the container is removed. However, if another call is received before removal, the request is routed to the existing container. If needed, OCI functions can scale horizontally to handle multiple requests simultaneously. Information about function invocations, including performance metrics, is displayed in metric charts within OCI functions. This allows users to monitor the behavior and performance of their functions effectively. To summarize, we've covered the key operations involved in deploying and invoking functions on Oracle Cloud Infrastructure. With this understanding, you are now equipped to effectively manage and monitor your functions on OCI functions, ensuring efficient and scalable operations in your cloud environment. I hope you found this lesson interesting. See you in the next one. Thank you for watching. Hello and welcome to this lesson on OCI functions use cases. I am Mahendra Mehra, your senior OCI instructor with Oracle University. In this lesson, we'll explore different scenarios where you can apply serverless functions in Oracle Cloud. So let's get started. Simply put, serverless use cases revolve around executing code in response to an event. Serverless use cases fall into several categories, and we'll discuss some of the key ones on this slide. The first category is event-driven governance. This includes scenarios such as audit logs and network flow logs. Imagine you need to set up an event based on an audit log or a network flow log to trigger a specific action. This action could involve reading the logs, filtering them, and forwarding them to a security incident management system such as Splunk. The next category involves web and mobile API backends. Here, an API gateway fronts a function that implements the backend code for a REST API. The API gateway then exposes this function as a REST endpoint to users. The third category is real-time file and stream processing. For instance, data might be uploaded to an object storage bucket or streamed via a Kafka-compatible service. This event could trigger a function to process the data and take appropriate action, such as analyzing the data and storing it in an autonomous database. Functions also find applications in machine learning, DevOps, and other areas. Let's delve into some specific use cases. OCI resources like compute instances, databases, networks, and storage generate resource change events via audit logs. By using a service connector with audit logs and functions, you can enforce security policies and governance rules. For example, you might want to ensure that no compute instances with public IP addresses are created. Using audit logs, a service connector, and a function, you can identify and shut down any non-compliant compute instances. Let's look at the second use case. Consider the OCI virtual cloud network that sends network access log to the OCI logging service. You can use a service connector with logging as the source and functions as the target. The function will parse the logs and send them to the third-party security incident management system like Splunk, ELK, or any other SIEM system. In scenario 3, insurance claims XML files are regularly uploaded to object storage, triggering an event rule configured to invoke a function. This function reads, transforms, and inserts the XML data into an Oracle database, such as one running on Exadata Cloud Service. The function service scales horizontally to handle multiple files being uploaded in parallel, ensuring efficient processing. In this scenario, we have an Oracle virtual machine of shape VM standard E2.1, which sends CPU and memory usage metrics to the OCI monitoring service. You can set an alarm in the monitoring service for high CPU or memory usage. When the alarm is triggered, it sends a message to a notification topic to which a function is subscribed. This function resizes the VM to the next higher shape available, such as from E2.1 to E2.2, ensuring optimal resource utilization. To wrap up, in this lesson we explored serverless use cases including event-driven governance, API backends, real-time file processing, and managing cloud resources efficiently using functions. I hope you found this lesson interesting. See you in the next one. Thank you for watching.
Hello and welcome to this lesson on prerequisites to creating an OCI function. I am Mahendra Mehra, your senior OCI instructor with Oracle University. In this lesson, we'll explore the key prerequisites for creating and working with OCI functions. These include setting up the necessary resources, creating the required IAM policies, and configuring necessary network settings and development environments. Let's start by looking at the service limits imposed by OCI functions. These limits dictate the number of functions and applications you can create within a specific region. It's essential to be aware of these constraints as they vary based on your payment method. Now let's look into the Oracle official documentation to see these service limits in more detail. I'm going to switch over to the browser now. Here we are on the Oracle's official documentation page for the functions service limits. Let's first look at the applications limit. As you can see here, the limit name is application-count, and this shows the number of applications you can create in a region. If you're using Oracle Universal Credits, the limit is 20 applications, and for pay-as-you-go or trial accounts, the limit is 10 applications. Next we have functions limit. The limit name is function-count, which indicates the number of functions you can create within a region. With Oracle Universal Credits, you can create 500 functions. For pay-as-you-go or trial accounts, it's 50 functions. Moving on, let's review the total memory for concurrent function execution. The limit name here is total-concurrency-MB, and this indicates the overall total amount of memory available to allocate for concurrent executions of all functions in the region. For both Oracle Universal Credits and pay-as-you-go or trial accounts, you have a limit of 60 GB or 180 GB for regions with 3 availability domains. And as shown, the actual memory usage will always be less than or equal to this amount. Finally, let's examine the total memory for provisioned concurrency. Well, provisioned concurrency is a feature that allows you to pre-allocate a specific amount of memory and processing capacity for your functions. This means that your function instances are always ready to respond to incoming requests instantly, without the latency that might occur when new instances are being created in response to increased traffic. For this resource, the limit name is provisioned-concurrency-MB, and for both Oracle Universal Credits as well as pay-as-you-go or trial accounts, 40 GB is the limit set. Also, as shown, the actual memory usage will always be less than or equal to this amount. It's crucial to understand these limits to effectively plan and manage your resources in Oracle Cloud Infrastructure. Now let's return to our slides. Additionally, each function is subject to a fixed maximum payload size, allowing up to 6 MB of data for both incoming requests and outgoing responses. These limitations are immutable, emphasizing the importance of optimizing data handling within your functions. As a tenancy administrator, your primary responsibility is to create OCI user accounts. Simultaneously, it's imperative to establish a group within OCI to which these user accounts will be assigned. These groups play a crucial role in managing access and permissions for function-related resources. However, if your tenancy already has suitable groups and user accounts in place, there's no need to create new ones. Before users can start using OCI functions to create and deploy functions, as a tenancy administrator, you have to create a compartment to own network resources, which includes a VCN, a public or private subnet, and other resources such as Internet Gateway or Service Gateway, a route table, or security list. There should also be a compartment to own function-related resources like functions and applications. Note that the same compartment can own both network resources and function-related resources. Alternatively, you can create two separate compartments for network resources and function-related resources. Before users can harness OCI functions for deploying functions, a VCN housing the necessary subnets must be in place. These subnets are where functions and applications will reside. The VCN, although not necessarily owned by the same compartment as other function-related resources, must have a CIDR block with sufficient available IP addresses for OCI functions to function effectively. Oracle recommends configuring security lists with stateless rules to facilitate the largest possible number of concurrent connections. Let's explore how CIDR blocks are used to specify IP addresses when configuring VCNs and subnets for OCI functions. As we delve into this process, it's crucial to note that the VCN must have a CIDR block that offers a minimum number of free IP addresses. This necessity stems from several factors that govern the functioning of OCI functions. These factors include the memory allocation specified for each function during execution and the maximum number of concurrent executions expected for that function. Additionally, considerations must be given to the collective memory usage and concurrent executions of all other functions operating within the same subnets of the VCN. For each function you expect to execute concurrently in subnets in the same VCN, identify the amount of memory that has been specified for the function to use while executing in GB. For example, if 512 MB has been specified for the function, use 0.5 GB. Next, you must determine the expected maximum number of concurrent executions of the function and multiply the amount of memory for the function by the expected maximum number of concurrent executions of the function to determine the function's total maximum amount of required memory in GB. Next, you must add together the total maximum amounts of required memory for every function that will execute concurrently in subnets in the same VCN to produce an overall total maximum amount of required memory in GB for all functions. Divide the overall total maximum amount of required memory for all functions by 14. Since each 14 GB of memory usage requires one additional IP address. For each subnet in the VCN, add 3 to the total number of IP addresses required, since 3 IP addresses are reserved for internal use for each subnet. Consider the following simple example with a single function and a VCN that has one regional subnet. Let's say that 512 MB memory, which is rounded to 0.5 GB, has been specified as the amount of memory that the function can use, and that you expect 2000 to be the maximum number of concurrent executions of the function. Let's also say that you expect all 2000 concurrent executions to be simultaneously using the full amount of memory specified for the function all at the same time. Here is the formula to calculate maximum required number of IP addresses. In this case, the function's total maximum amount of required memory is 1000 GB, that is 0.5 into 2000. Since there is only one function, I'll strike out the calculation for other functions. In case there are more functions, you must calculate the sum of all functions' maximum memory requirements. The number of free IP addresses required for concurrent executions of the function is 72, that is 1000 divided by 14, and the number of IP addresses reserved for internal use is 3. Since there is only one subnet, we are multiplying 3 with 1. Therefore, 75, that is 72 plus 3, is the minimum number of IP addresses that OCI functions require in the VCN. Using a CIDR calculator, you can see that a /25 CIDR block is sufficient for OCI functions use of the VCN. Since a /25 CIDR block has 128 distinct IP address. Since this lesson is getting a bit long, I'll pause here and we will continue in the next lesson.